later this weekend. Okay, today is one of my favorite topics, linear regression. And you've probably seen this before in high school. If you haven't, don't worry, we're doing it from scratch. The beauty of linear regression is it allows us to look into the future, to make projections and predictions, and it has a rich and deep and wonderful history because we've been trying to find mathematical methods for predicting the future for a long time. And this is one of those things you can master quite easily and use in your everyday lives. Not that you will, but you could if you wanted to. So one of the fun projects that I was doing recently was trying to predict the winners of game shows using linear regression. So I had a student in this very class 2 years ago. What we did was we attempted to predict the winner of The Biggest Loser. You know the TV show The Biggest Loser? You lose a lot of weight. Using a multiple linear regression and factors that the contestants start out with, like their starting weight, their ages, and their the genders and things like that, and using the data from previous seasons to see if we can predict who the winner was this season statistically. And it works, right? So you can do wonderful things with it. And before we get there, though, let's begin by reviewing what we looked at so far. When it comes to comparing two continuous-ish variables, I say continuous-ish because we have interval, ratio, and maybe ordinal data that can be considered continuous. All right, so when you're comparing those two things, we like to do correlative analyses. And we've looked at, a few weeks ago, Pearson's rho, which is a correlation between two interval level variables that attempt to assess something resembling linearity. Let's make sure I'm recording. It'd be really sucky if I'm not recording. Recording good. And then we looked at Spearman's rho last time, and Spearman's rho, as you may recall, attempts to measure or describe a relationship between two ordinal variables, rankings in other words. And we looked at Kendall's tau, even though we won't be doing Kendall's tau in this class. Kendall's tau does a similar thing to Spearman's rho, but also allows us to compare an ordinal variable with an interval or ratio level variable. And that is the equation for Spearman's rho. Hopefully you've done the homework assignment that I uploaded. It's not that hard, it's just mechanical. You go through the spreadsheet. Very simple. We look at differences in ranks. I mentioned Kendall's tau, it's a different method. We won't be doing it in this class, but I want you to know what it is. So, moving on from correlation is another way to describe relationships between two continuous variables. That's regression. And the story, as I mentioned, goes back hundreds of years, and some of the key players, and by the way, I don't require you to know the history. It's just a fun little thing to point out that this is an evolving science, and that a lot of what we know about this is actually fairly recent. So Legendre was one of the first to describe the method that I'll be showing you today called the least squares method. And a lot of this stuff, like almost all of statistics, comes out of astronomy. Legendre was doing several things. Among them, he was attempting to measure the size of the world, or project or predict the size of the world based upon other kinds of observations. And to do that, he needed an estimate of precision. He invented this thing that we're going to look at today called the least squares method. In addition, Gauss, we've heard that name before. Gauss is possibly the greatest mathematician who ever lived, and that's what he would tell you anyway, because his ego was quite huge. And he also had worked on a method of least squares analysis that we'll talk about today, around the same time as Legendre. And even though Legendre published first, Gauss said, actually, I did this years ago, and here's my evidence for it, because he does that a lot. Right? And so the world tends to agree with Gauss because he could actually prove that not only this method that I'm going to show you, but to show that how it reacts and relates to the normal distribution and things like that. Gauss used the method we're doing today to predict the existence of an asteroid. The asteroid's name was Ceres in 1802. Ceres is the biggest asteroid in the asteroid belt, Ceres and Vesta. So in 1802, using linear regression, he says, according to these, the data surrounding other planetary bodies in our solar system, there should be another planetary body right there in that part of the world. In fact, if you go to astronomical charts from that era in time, they have Ceres listed there as a planet because they expected fully to have a planet there. But he was right. So when the observations came out, the astronomers found there was a large body, exactly what he predicted, based upon, again, the method that we'll be doing today. Isn't that exciting? And other people have used this method to predict wobbles in the moon's position around the world, and Laplace, another famous mathematician, who you may learn about if you do advanced calculus, used it to investigate the relationship between Jupiter and Saturn, their positions relative to the Earth. My background's in physics, so I'm a little obsessed with this stuff. Right? But be aware, it has a grand implications beyond the examples that we're going to do in class today. Grander implications about the nature of reality and the cosmos and so forth. So, as I mentioned, Gauss and Legendre both developed a technique for describing the motion of planets, and they ended up calling it, or someone ended up calling all of this, regression. The term regression comes from biology, from an observation made around the same time period that living things tend to regress to an average size. For example, if I measure your fitness levels today, and you get an average amount of fitness level, let's say how fast you can run up the stairs, and I take the 3 or 4 of you who have the absolute best fitness levels, and I test you again next week, what's going to happen, do you think? It's going to go down. And I take the absolute worst of you, and I test you again next week, what's going to happen? You're going to go up, exactly, because the extremes tend to regress to the average. And that's really what Gauss and Legendre were showing, is that these extreme observations regress to an average. And we're attempting to measure what that average is. And if we can measure that average, we can follow that average through time and predict the future, just like Gauss predicted where the asteroid Ceres would be in 1802. So, in statistics, regression means using observations and constraining them to that average, assuming they're going to regress to a common value clustered around a certain average. And the way that we constrain them to behave depends upon our imagination very much so. You can constrain these observations to behave in any shape we like, a curve, a circle, a straight line. Usually we choose a straight line. There's no reason. I will show you one way to justify that, but very often we choose a straight line because our imaginations fail us. All things are linear. A relationship between a car and its the time a car travels and its velocity, that's a straight line, unless it's accelerating, then it's a curve. But we tend to think about the straight line. Right? So what we're doing today is linear regression, meaning that we're going to constrain our observations to behave as if they are a straight line. With a straight line, we can project that easily into the future and make predictions. Okay. So regression, the textbook definition, techniques used to analyze relationships between variables and to make predictions. There are many kinds of regression. We're doing linear, and I mentioned different kinds of shapes. In advanced statistics, it's something called logistic regression, which is what every epidemiologist does. A logistic regression is an attempt to associate a variety of variables or predictions with a dichotomous outcome. For example, I've used logistic regression to predict, we're doing right now the grad student, predicting which MMA fighters will get concussions. That's a dichotomous outcome, concussion versus no concussion. We're looking at various factors, their age, their gender, how long they've been fighting, things like that. So that's the powerful things you can do regression. I've used linear regression to predict or to estimate how many deaths the polio vaccine has saved in Canada. So what we did was we looked at how many deaths were happening in the early part of the century, drew a straight line to see how many deaths there should be today, and how many deaths there really are today, and that difference is how many deaths were saved. But we use that regression to project into the future what that original data would have told us if vaccine had not come along. I have a colleague, Dr. Pravad Jha, who used regression, linear regression, the same technique you'll be seeing today, to predict how many girls should be living in India today. And then he subtracted that from the number of girls that actually are in India today and found there are 13 million missing girls. And this made global news because he concluded from that in fact selective abortion was responsible for these millions of missing girls. So these are very powerful techniques you can use to answer all kinds of interesting policy questions. All right, off on a tangent. Tangent? Straight line tangent? Okay. In terms of linear regression in this class, we care about two types, simple and multiple. Today we're going to do simple. Later on, we're going to introduce the idea of multiple. Multiple regression looks at a variety of predictive variables that may be associated with the straight line we're going to build. Simple looks at just two things. So two things are going to be correlated. So simple is what we're doing first, obviously. So simple. Here it is. And that's, you've seen that style of equation before in high school, one assumes, right? You've probably seen it as written a different way. Do you remember how it was written in high school? What letters we used? mx plus b, exactly. And there's a reason we write it this way and not mx plus b. And we'll show you that reason in a second. So this is the multiple equation, the multiple regression. So you can, where's my pointer? You can kind of already see that this resembles that in this first part. This first part resembles that. The multiple part is when these other terms are added on. Okay. So you find like most of advanced mathematics are just building on from high school math. The notation, the terminology, what am I trying to say? I've got words today. The terminology and the notation have to be modified slightly to account for the greater complexity. So mx plus b is what you're used to in high school, where m is your slope or gradient, and b is the y-intercept, or the point at which the line crosses the y-axis. Hopefully this is all coming back to you. That's the way it looks. M, there's your slope, there's your b. Okay. So how do you find m and b? Well, b is easy. That's the point at which it crosses the y-axis, and the slope is just the change in y over the change in x, the rise over the run. Okay, hopefully that terminology is coming back to you now. Okay, so here your slope is that divided by that, so slope here is 2, and the b is 1, that's where it crosses the y-axis. So here the equation would be 2x plus 1 would define that straight line. Grade 10 stuff, easy stuff. Again, we don't use mx plus b, we use alpha plus beta x. And the reason for that is, as we add more terms, these alphas and betas become several alphas and betas. We can't have several m's and b's, just several alphas and betas, right? So alpha is the y-intercept, the equivalent of b, and the slope is beta, equivalent to m. Right, so don't get confused if you see these things being transposed. That's all. Anything before the x is the slope still. The textbook uses a plus bx. Why? Because they're the textbook. They do things differently. So, and for some reason they don't like alphas and betas, so they write a plus bx. And it's kind of useful because when we expand it, we have a bunch of b's, so b1s, b2s, and all the way outwards, but just still one a, one constant, which can be considered to be a type of y-intercept, and so forth. This is a linear expression. If I were to graph this, would I get a straight line? Probably not. Probably not. We still call it a linear expression. You know why it's called a linear expression? It has to do with mathematical terminology and notation. Anytime the x's have no exponents, or it's x to 1 here, it's linear. It's a linear equation. If it's x squared, then it's a different kind of equation. If x cubed, then it's a different equation, and so forth. If it's 4, it's a quartic equation, and so forth. So all linear means is that it's x to the 1. The x has no exponent on there. So don't get confused if you see something referring to a linear equation, which really isn't a straight line. And I'll try to minimize that kind of confusion. Okay. So with linear regression, we have a bunch of values for x, and we try to figure out what the best values are for the y-intercept and the slope, such that we can get a straight line that most closely resembles our data. And hopefully now, if you're thinking about this really cleverly, you start to ask yourself, how do you determine which straight line is the best representative of my messy clustering data? Right? Because there are probably several ways to estimate that. So any straight line can be described by this equation, any straight line in the universe, and y, of course, is the values of one variable, x is the values of the other variable, these are the intercepts, and so forth. Okay. Now, in this class and in the textbook, y prime is the predicted value of y. So after I make my equation that supposedly describes the relationship, even though it's not going to be precise, it describes the relationship going off into infinity, any predictions made by this model have a prime, a y prime. X still is the same old real value of x, and the a and the b remain the same. Now, we don't call the b the slope anymore, we call it the regression coefficient. And the reason for that is, once we move into multiple dimensions and multiple terms, you can't visualize a slope anymore. It doesn't have any real-world graphical manifestation or importance. It's just a coefficient, something that goes before a variable. So put slope out of your mind, unless you need to think of it that way, but be aware that we call it the regression coefficient. The thing before the x is the regression coefficient. So what we're going to need to do our calculations are means, deviations from the means, and these things called cross products. So for the time being, consider cross products to be just multiplications, but cross products are actually vector products. As we move on to multiple dimensions, the cross products aren't simple multiplication anymore. However, for the purposes of this class, just consider them to be multiplication. So we remember what deviations are. Well, we did standard deviation. A deviation is just the difference from each observation from their mean. Okay, so let's say I want to predict how well you are going to do on your final exam based upon how you did on the midterm. And in fact, I am going to do this math because that's the kind of thing I do for fun. So see if I can actually predict how well you're going to do. What do I need? I need to be able to predict for each of you individually. So if I have your midterm mark, I have to have a machine. I plug it in there, and I say, Bob's going to get a 65 because he got a 62 in the midterm. Excellent. All right, so I need a fairly robust, a fairly tight little equation to get me that result. Kind of like what I did for the Biggest Loser. We created an equation, and for Cynthia, who's in season 12 here, we have her gender, we have her income, we have her starting weight. We plugged in all those variables, and we got her expected weight loss at the end of that. All right, so that's what I want to do. To do this, I need to construct a model. And in the model, there will be a slot for your midterm mark. And I put in that midterm mark, I crank the model, and I get a final mark. What is a model? It's just an equation. It's my y equals a plus bx equation. That's what the model is. How does one construct a model? Construct any kind of model, whether it's mathematics, whether it's in science, whether it's in political science, whether it's in sociology, any kind of conceptual model or mathematical model, you need sample data. So, in other words, when I did The Biggest Loser, to predict who's going to win The Biggest Loser from season 12, I used seasons 1 through 10 as my sample data, created my model, and assumed the same characteristics applied to season 12. So, if I'm going to predict how you guys will do in the final, I need sample data. So I'm going to use the previous years. So the cohorts that came before you, how they did in their finals relative to their midterm, and use that information to predict your outcome. Obviously, there are going to be some conceptual issues here. You are not the same people as them. Maybe you're smarter than them. Maybe the education you got in high school is better than their education. Maybe I've become a better teacher since then. Or maybe the exam is different. All these things may have changed. So there's a lot of wiggle room here. This is not a game of precision. It's a game of estimation. So here's my data. This is last year's class, let's say. I've got 10 students, and this is the midterm mark. Well, let's say the midterm mark is 1 to 10. There's no reason. I just made this data up, right? It should be 1 to 100, but let's say it's 1 to 10. So student 1 got a crappy 2 out of 10 in their midterm, and their final, they got a crappy 3 out of 10. But there's some improvement. And let me see. Student 6 there did really well, 9 out of 10, but actually she went up, got 10 out of 10. Everybody go down? Let me see. It went down. 4 went down. There. Okay, good. So 4 went down. So he or she had a bad day, let's say. So there's some fluctuation. So I'm going to use this information to construct the model, the regression. How do I know what shape that relationship should be? Well, we know it's going to be a straight line because that's what we're learning today. But if we're not in a classroom environment, how do I know it's going to be linear? I can create a model for a straight line, a parabola, something monotonic. You saw monotonic last time, monotonic relation like that. Let's plot it and find out. So my sample data, I plot and I see that. That looks like a straight line. Looks linear-ish. Yes, pomosity, right? So if I were to actually draw a line through here, I can easily draw a straight line that resembles those points. Now, ever do a Fourier analysis or a power series analysis? Anyone know what those are? Okay, so no math geeks here. So there are other things in math you can do, like a Fourier analysis uses a variety of trigonometric functions to create this incredibly clunky equation that will go through every single point. A power series does a similar thing. A power series uses a series of polynomials that do a similar thing. Everything. So mathematically, it is possible to create an equation for a line that goes through every single point. But that's not useful. Why is that not useful? Why would I prefer a straight line rather than some fancy curve that actually fits my data perfectly? Yeah. Yeah, outliers too, that's one thing. Very good point. What else? What am I trying to do eventually? Yeah. This shows the average. Yeah, yes, and why is that important? Why? No, you're almost there, yeah. I'm trying to predict the future, exactly. So if I get a precise curve to go through absolutely every point, okay, how does that allow me to predict the future? It probably continues on, right? It has no relationship to the relationship. That's what I care about. It tells me everything I need to know about these data, but these data are sample data meant for me to estimate the world of students. So a straight line allows for the fluctuations along the way and allows me to predict in the future, again, with a similar amount of fluctuation along the way. It's entirely possible this is actually like a parabolic, or actually a modified sine wave going this way, and I got it entirely wrong. That's possible too. But we're not going for absolute precision here. We're going for some sense of prediction. So keep in mind that these are the observations, and here's what we're fitting. How do I know where to draw that line? These are the things that Legendre and Laplace and Gauss figured out. They figured out that I need to draw a line here that satisfies, that goes through most of these points, or a large number of these points, but the ones it doesn't go through, the distance from each one to the line has to be small. So the average distance has to be small. If I could easily have drawn a line over here, through that point, whatever it might be, and some of these would not touch the line, but their distances would be pretty small. Okay? So, in other words, there's a variety of ways of looking at this. The technique we're using today is called the least squares method. That's the most popular, but there are a variety of methods. We can attempt to minimize the distance vertically from each point to the line. We can attempt to minimize the distance horizontally from each point to the line, or we can attempt to minimize the difference orthogonally from each point to the line. The least squares method, I think, attempts to measure it vertically from the line. Doesn't matter. I mean, it's useful stuff for you to know, but it's not important. Yes. It doesn't matter. What matters is how far above or below. Now, it's a good point because the fact that this one's above the line is countermanded by the fact that that one's below the line, and this one's like twice as far. So, so two above about the same distance. That one's twice as far, but one below. So this one kind of accounts for these two. So there's balance. Right? That's kind of how the technique works. Again, this is not the only kind of technique for linear regression. It's just the one that we're going to do and the most popular one. So, the sample data shows us something resembling a straight line. So we're going to attempt to model a straight line through it. When we can get a straight line equation, then I can plug in any value of midterm into here, blah, 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 and get the projected or predicted final exam mark out of here. It's not going to be precise, but it's going to be close, right? So I want the best possible values of A and B that gets me the closest prediction to reality of the final mark, right? I mentioned, how do I know which line to draw? Well, here's this picture points out the distance from each point. So distance 6, distance 5, distance 4, distance 3. If I take the average distance, which Like, okay, I take the average difference of this line, I draw another line, take the average distance of that line, another line, average from that line, I draw an infinite number of lines and compute the average distance for each set. Which one gives me the smallest one? It's a calculus procedure, really, because I'm taking infinite numbers and minimizing distance, but you don't need to use calculus for it. The least squares method actually minimizes, see that number here? Minimizes the sum of all these distances. Notice it's distance squared. Why is it squared? Yes. Get rid of the negatives, exactly, because these ones are going to be positive, these will be negative. So I square them, add them all up, and that's my total square distance. So I want the least square difference, hence the least squares method. It seems so obvious and simple, but it took, several of the greatest minds in the history of mathematics to figure this out. So here's our data. We have each student's here. We have the midterm marks are over here. The final marks are over here. Again, we are using these data as a sample to construct the model that will then be used to make predictions. Something students kind of get messed up on occasion and get asked, but why are we trying to predict the final? We already have the final. No, we have the final for this set. I haven't got the final for you guys. I'm going to use these data here to predict your outcome. So here are my students, here are the midterm marks, here are the final marks, and here I'm going to compute the average midterm is 5. And here I'm going to subtract each of these from 5. I'm going to square that and get up something over here. And here I'm going to do the same thing, but I'm going to take each of these and subtract it from the average final mark. And I get that. So notice that the sum is always 0 because the sum of deviations is always 0. Remember that from our standard deviation example a long time ago? So I've just subtracted each of these from the average, same here. Now I'm going to square these. Here I didn't square it. Here what I'm doing, I'm multiplying that number by that number. I'm getting that. Okay. Now then I do is I take these sums here and I plug them into that equation. I get that. So it's mechanical, yes. Right. Yes. Let's make sure, yes, that is correct. Let's make sure I do that again. I think it should be in my sign, actually. I think I may have done that one wrong. I better check on that. That's a good point. I better check on that. I think it should be minus. I may have screwed up. So if I don't fix this, is it minus 3? Oh, look at that. I did it right. Okay. Shit, okay. Oh, all right. Oh my God. Yeah? No, I think you keep the minus in. Yeah. Thank you. Yes, 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 yes. If you find any problems with this, it means I've screwed up somewhere. Let me know instantly, okay? But yes, you keep the minus in. So that's that times that. That's right. So everything's cool. Everything's cool. Okay, right. Whew. So, right. So it's these green numbers that I care about. The sum of the x squares and the sum of the xy's. And I plug it in here, and this gives me my b, which is the slope. Now, you may get confused because high school, the b was y-intercept. Here, b is the slope. A is y-intercept. So I get a 0.9 as my slope, or my regression coefficient. And for A, to compute A, I'm going to use the b that I just computed and just plug it into this equation. I'm going to use sample data, but the average sample data. So the average x and the average y, and I get 1.5. And now I can just plug those numbers in to get my model. So here is 1.5 plus 0.90x gives me my y prime. Y prime again is the predicted value. So anytime I plug in the midterm mark for my sample into here and multiply it by 1.05, I should get something resembling the final mark from my sample. It won't be precise, it'll be resembling it because the line has been kind of modulated. Okay. So in other words, final exam mark equals that. Okay. So now if I have a student who got 6.5 on his midterm, on your, let's say it's one of you guys, on your midterm, I can expect you to get 6.5, plug it in here, to get 7.35 on the final, based upon previous year's experience. That's all we do. We're using previous data to predict what the current crop will do. Very straightforward stuff. Okay. Do you see any issues with robustness? Robustness means, will I get the same answer every time I do it? Yes. I'm sorry? Outliers are a huge problem. So why are outliers a problem? That's right. So if we go back to our straight line with those points here, one point over here will have moved my straight line from here. One guy would have done all that. So one of the things we often do is go through and remove the outliers, the extreme outliers, to make sure everything gets flattened out. But also, yes. Well, if I give you an assignment for it, I will say to compute the extreme outlier. Otherwise, I'll say just, if I don't tell you, just do it the way it is. But to do this in practice, like the most useful, the most proper thing to do is to compute the outliers. Okay. So to show what I mean by robustness, we're going to look at something called Anscombe's quartet. Again, I don't need you to memorize Anscombe's quartet. It's just for your education. It's not something that's covered in the textbook at all. The Anscombe's quartet was 4 data sets that were put together by Anscombe to show the problem with linear regression. How if you just looked at the straight line, it may not tell you what's really going on. So in these 4 data sets, we have exactly the same regression equation. They've been gone through the same process we've done. We've got exactly the same equation. The mean in each case is exactly 9. The variance in each case is exactly 11. The mean of the y's in each case is 7.5. The variance is exactly the same. The correlation between the 2 variables in each case is exactly the same, very high, 0.81. And the linear regression in each case gives us y equals 3 plus 0.5x, okay? So in each of the cases I'm going to show you, everything that we compute is exactly the same. So you're probably visualizing a straight line for each case. But, here's the data, okay? Here's the first one, not bad, nice straight line. Here's the second one, well that's weird. Same straight line, but the data clearly is not linear. It's curvilinear, we call that. And we'd actually model that differently. Here's the third one. Well, that's the outlier, as you mentioned, right? So it's very linear, but that guy's up here. Gave me exactly the same line. And here's the last one. Definitely not a straight line. Bunch of guys clustered here, one guy over there. But if I model this the way that I've shown you using exactly the same equations, I get a straight line. That's the same. So I'll go back quickly. See, all 4 exactly the same line, but different data. So what's the lesson here? The lesson is, it's just a tool. Regression is just a tool that attempts to model the data as if it were a straight line. It does not necessarily reflect reality. The underlying data may in fact have nothing to do with linearity. So it's a bit of a dangerous game sometimes, but it's the tool that we have, it's the tool that we use. So outliers have a dramatic effect, as we saw in that last example, in the final model. So very often we check the data to see if outliers exist, and we remove them. Right. There are things we can do to determine the robustness, the quality of the data, of the fit. We call that a diagnostic. We look at the goodness of fit. We look at whether or not we've done things appropriately. Next class, we'll look at the diagnostics of linear regression. In SPSS, Monday you'll be doing this. Just very simple to do. Go to Analyze, Regression, and Linear. That's your homework. Any questions about linear regression? A fun topic, a good topic, a useful topic. There you go. Cool. I will upload the audio later.